the cloud. Perfect. Thank you everyone for joining. This is fantastic. I've been looking forward to hear for this talk because it's a very interesting topic. Roughly around restoring statistical validity in group analyses of motion corrupted MRI data. So we have here Dr. Antoine Lutti, or Lutti, I think I'm murdering the name. I should have looked it up, I'm sorry. Yeah, he's currently an assistant professor in MRI physics at the Laboratory for Neuroimaging Research, Lausanne University Hospital in Switzerland. His main research interests are development of novel quantitative MRI biomarkers of brain microstructure, pulse sequence development, and related areas. And he's also been the technical director of the MRI platform of the clinical research department at the hospital since 2013. Prior to this, he was a postdoctoral fellow at the Wellcome Trust Center for Neuroimaging, University College London, working with Professor Nicholas Wiskoff. Yeah, so without further ado, maybe I should mention he did his PhD at the Victoria University of Wellington in New Zealand, working with Professor Paul Callahan. So without further ado, Dr. Antoine Lutti, take it away.
Thank you, Pradeep. You can call me Antoine, that's fine. We're amongst friends here. So we'll keep that casual, shall we? So I'll start by sharing my screen so you can see what I'm talking about. There you go. Can you see my screen? Yes. Okay. Very good. So thanks very much, Pradeep, for the introduction and for inviting me for that talk. I'm delighted. I'm part of the working group. I enjoyed the emails bouncing back and forth. It was interesting. I try to take part in places, though not very often. So today I'm going to be talking about using a quality control metric in the statistical analysis of MR data affected by motion artifacts. Okay. So to start with, and we all know this already, I mean, motion artifacts are ubiquitous in MRI, right? And they affect all sorts of brain measures that we might want to extract from brain images. Okay, so that's relevant for morphological measures like cortical thickness, for example, but also functional data like resting state. Okay, so I'll refer to the previous NIQC lectures that were given over the last weeks by Tonya White and Jamie Henson, because they talked about all this a lot better and in more detail than I would do, right? So that's for starters. Now, in order to sort of stay on top of motion artifacts, I mean, so people have looked at the quality control of MR data for quite a while now, and I think it's fair to say, although people might have different opinions, I don't know, that visual assessment is still the gold standard. But that comes with a number of issues. One of them is reproducibility, because it seems to me, going through the literature, that you know, no matter how sort of stringently and you train the raters, there is always a degree of inconsistencies between them. The second point is sensitivity. It's been shown that, you know, there might be a small level of motion artifacts in the data that would go unnoticed in a visual inspection, but they are still sufficient to yield significant impact on the morphological measures of the brain. And the third point is that it's very labor intensive, right? So you have to put a lot of effort into training people, and then you have to go through the sort of painstaking process of examining the data, which can be really cumbersome given the size of data sets these days. So to overcome these problems, so people now are working on sort of image-based measures of data quality. So the plus side on these is that, you know, it's quantitative and also automated, so that alleviates some of the issues with visual inspection. However, and I think this is quite a general statement, and you know, someone might think otherwise. I'll be delighted to hear it. But I think I found quite a few empirical validation of these measures against the actual history of the motion during examination. Sorry, I should have switched off my phone. And the second point, the last point is obviously these measures being image-based, they inherently depend on all the features of the image. One being the contrast, like a flare T2 weighted image or an PRH image like T1 weighted, and also things like resolution. Now, this is not quite what I'm going to be talking about today on, the pros and cons of different metrics. I mean, the thing that I'd like to discuss with you today is what people do with the quality control measure that they've got on their data, okay, and how they use it prior to subsequent analysis. As far as I'm aware, the current practice today is still to sort of label the data into two categories. So you'd have the accept category, which is deemed acceptable for analysis. And the last option is the exclude, which is the data that you basically decide to discard and put aside, okay? And to illustrate the difficulties with that, I've taken the liberty to take a screenshot of Jamie Henson's presentation a few weeks back, okay, that illustrated exactly what I mean. So he showed like a distribution of visual scores of MR data across a range of raters. And then the question that he asked was, okay, I've got these histograms now, and where do I put my threshold to separate the accept category and the exclude category, right? And that is a very difficult thing to say, like he explained. So that's one limitation. The other problem is, I mean, if you look at the effect of motion on typically morphological measures, I mean, it's a continuum, isn't it? So you have it increases gradually as motion increases, and somewhat it seems like binary labeling of the data might be suboptimal. Yeah, so that's what I'm going to talk about today mostly, right? So we've developed a method that we call the QUIQI, and the goal of this method is to insert like a motion degradation index, so like a quality control measure specifically targeting motion degradation directly into the statistical analysis of the data. Okay, and I'll show you how it can help ensure the validity of the statistical inference and ensure optimal sensitivity. Are we okay so far? Yeah. Okay. Right. So the original postulate for this
Sorry,
is that.
Did you ask a question? Or?
Who, me?
Yeah.
No, I just asked if someone had comments to make on all these.
Oh, okay. Okay.
It's welcome. I mean, we can talk about all this, but okay, I'll just carry on. So the overall postulate is that head motion increases the level of noise in the MRI data. Okay, one I think reason for that postulate is that the motion artifacts, they act as a spatial modulation of an image. I mean, it could be argued this is the definition of an artifact, and they tend to increase the more motion takes place during the acquisition of the data. And also, I think another feature which I think is very interesting and useful is that no motion artifact look alike. Okay, that's because the exact sort of features of the motion artifact depends on a lot of the details of the occurrence of the motion, when it took place, the hardware, head coil, magnetic field, and the rest. Okay. So,
quick question. Do you think the leftmost image is actually good? It does not look very good to me. What modality is this?
That's an R2 star map. So I'll be talking about R2 star maps all the way. Yeah. So it's not a T1 weighted image or anything like that. Yeah. So that's what, in the context of what I'll be presenting today, this is a good image. Okay. It might not be a good image in terms of the contrast between white and gray matter, for example, but at least it's artifact free. Yeah.
Yeah, see, that's an important point, because what is good depends on the goal, and what is being measured. I think you touched upon it quickly, but this seems it's usually forgotten sometimes,
Yes, yeah, absolutely. Yeah. So I mean, for the kind of data, grade to what matter contrast isn't really of the essence. I mean, I'll describe the data a little bit better in a few slides down, I think. So the postulate is that head motion tend to increase the noise level globally in an MR image. Okay, and so it happens that in most analysis software there is a tool that's called ReML, so it's restricted maximum likelihood. Okay, and it's designed specifically to model inhomogeneous variance across the data set. Okay, so typically it's used for population inference with functional or structural data. Okay, so I'll guide you through what ReML typically does, and I'll show you how we can hack into it for our own purpose. Okay, so say you could take the case of like a group comparison. Okay, between a group of controls, that would be group 1, and then you have a group of patients in group 2. Okay, so what ReML lets you do in general is to define a set of basis functions, okay, specifically for each group. So these two basis functions are orthogonal, okay, and when you throw these basis functions into ReML, it will compute for you a noise covariance matrix, which is it's an estimate of the noise level in the two groups. Okay, so you've got two terms in this diagonal matrix. And each of these two values along the diagonal reflects the noise level into these two groups. Okay, and once the ReML's done that, the next step is to calculate weights for the data, okay, which are just the inverse of the noise covariance matrix. Okay, so you end up effectively with a weighted least square analysis. Okay, with a very specific case where you have only two values along the diagonal, one per group, so to say. Is that clear?
What does ReML stands for? Sorry, I missed
It's
it.
restricted maximum likelihood. It's a Bayesian concept. It's used. It's under the bonnet in most analysis software. You could take FSL, SPM. They all have it. Any software that will allow you to do like population inference and model inhomogeneous variance across a data set. You could, for example, the typical case would be, you've in a group comparison where you have patient groups that would move more than the group of controls that would be more compliant.
What do we take as our noise measure in anatomicals, right? Because in fMRI it's kind of easy, right? You have multiple dynamics, so you could get like sensible. What is the noise, right? It's deviation from the mean. But in anatomicals, we have one sample typically, right?
Yes.
So what do we take as our noise outside of the brain?
You have a lot of voxels. I think so. The ReML, what ReML typically does, at least in the implementation SPM, it looks at your design matrix. So your design runs an analysis on it, takes all the significant voxels, and uses that to estimate the noise.
But if it's two groups, that's what I don't get. So do we just consider any unique to the participant variance to be noise? Or how do we tell apart, real noise from something which is still could be, inherent to specific to the subject, right?
Well, I think that's a very good point. I think noise in that context is probably everything that is not explained in your design matrix. So typically you have a design matrix in which you include all potential contributing factors. Could be disease stage, could be drug dosage or sex or head size, whatever. Okay, so you model everything in there, and the noise will be basically everything that's not attributed to your design to your model, pulled across all voxels. Does that make sense? Yeah.
Yeah. So it's just kitchen sink of everything unexplained.
Yeah. Okay. So I'm not. So I can't be. I probably wouldn't be able to tell you the implications of this exactly, but yeah, I could probably find a reference for you. But I think that's how it's done. It's basically noise is basically everything you can't account for according to your model.
Do I correctly understand that it's only one value for all subjects in the same group?
No, so yes, so in the current, so if when you run like some sort of population inference, like like a second level fMRI analysis or some sort of a structural study, typically you assign the same basis function in group level per group, yeah, because you have no better information, if you like, yeah. So what you end up here, the dichotomy in the noise correlation matrix comes from the fact that the corresponding basis functions are orthogonal. Yeah. So in the weights, which are the inverse of the noise correlation matrix, you have the same value for all the diagonal terms belonging from the same group. Yeah. So it's a weighted least square, but it's like a, I don't know if I could say trivial, but it's a weighted least square with 2 weights in it. Okay, that's what it does. Yeah. Are there any more questions? No?
Yeah, I think we'll probably have to read the paper to get all the details right,
Yeah, but that's
Yeah.
I mean, what I'm trying to say here. I'm trying to introduce the main idea, so I'm going to
Yeah.
hack into it for my own purpose. Yeah.
Right. Yeah.
So
Exactly.
that's how it's used generally, and it's really widespread. I mean, people who do functional studies, they do that all the time. Yeah. So it's a way of accounting for non-uniform variance. The patient group being showing more noise typically, and that keeps your statistics in check, if you like. Yeah.
Right. So maybe a tangential question here. So the whole thrust of the paper is that you can account for noise, right?
Yes. Mm-hmm.
Is there a way like you estimate the noise like motion and then account for it in this context?
Exactly. You'll see it. It's on the next slide. Yeah.
Oh,
Yeah.
okay, my bad. That's what I was
Okay.
thinking that.
Okay. So this is how we go. So now, okay, this is about how we're going to sort of tweak the tool for our own purpose. So here on this slide, I'll first consider the standard case. Now I'm looking at the one like a one sample sort of t-test analysis. Okay. Well, I'm putting aside the group comparison because it just complicates matters, although it works just as well. So in a standard analysis, where you look at, say, the effect of disease evolution on the brain, or drug dosage, or aging, or something like this. Okay, so now one sample t-test. You start with a standard analysis. In that you only have one group here. Okay, so you assign the same basis functions for all the data sets. The noise covariance is uniform, and the weights are the same too. Okay, so in that case, you end up with an ordinary least square. Okay. Now, what we're going to do with QUIQI is we'll define a set of basis functions, however they might be in detail. But the idea is to insert a basis functions that are computed from an index of motion degradation. Okay, of how much motion artifact there is in it. Okay. Now, there might be a varying number of basis functions. They may have different forms depending on the problem at hand exactly. But the idea here is that you define these basis functions from the index of motion degradation, your quality control measure, if you like. Yeah, I think.
Basic question for anatomicals, what would be how do we deduce how much motion was during anatomic? How would we quantify?
So typically, the motion degradation index, it would be your quality control measure.
So
Right.
it's subjective rating of the
well,
rater,
I mean, I think in the case of subjective rating with visual assessment, in principle could work, but that probably wouldn't be continuous. So you might have a problem with that. But if you look at the UK Biobank data, or all the machine learning feature that they've done, or all that's been done in terms of image-based index of image quality would fit in there. Okay. Yes, and then the nature, the form of the different basis functions depend on the problem at hand. I'll show you how to do it, but that's the overall idea. In these basis functions, you insert basis functions that are functions of the motion of the motion degradation index. Yeah? And then you throw this into ReML. Okay, and so ReML, though it does what it normally does, so you compute a noise covariance matrix. Now you see that I mean, first of all, the matrix is diagonal because there is no noise correlation between data sets. But along the diagonal, now you can see that the term varies from one subject to another. Okay, so you have a noise specific, data set specific estimate of the noise. And therefore, you also end up with a series of weights that are also specific for each data set. Okay, so typically in that W matrix here, a high value like yellow typically would indicate a data set for which the motion degradation would be low. Okay, if the data is good, you give it a high weight. Okay, now conversely, if the weight is low, like dark blue, for example, okay, that would correspond to a data set for which the motion degradation index is poor. Right?
Quick question. So basically, are we trying to weigh different subjects based on a quality index that was computed earlier?
Yes, exactly.
Right, and optimized for that particular data set in the ReML framework, right?
Yeah.
If I can like really dumb it down, even maybe inaccurately, it's just a weighted linear combination of data set for a particular
It's exactly what it is. Yeah, it's a weighted least squares. Yeah.
Okay, okay, I see. So you're accounting for that by basically downgrading bad quality data.
Yeah.
In a way.
Mm-hmm.
Speaking very high level, right?
Yes.
I mean, that means it's very important that we actually get the image quality estimate right.
Yes, absolutely. Yeah.
Especially if it's continuous.
Yes.
Actually, I mean, on all the cases, and like you already pointed out, binary labels are not going to do much help for us because, you know, there's a lot of subjectivity, lack of reliability and whatnot. Decisions are made for different purposes, you know?
Yes.
So, but the framework of weighted linear combination has its limits, right? It assumes that the analysis is done in that way, you know?
In what way?
As in, like, here, for example, expectation maximization, you know, that only analyses that generally fit in this particular framework will this be applicable, you know, right?
Okay.
So what I mean is that, for example, sometimes, although these acceptable or not decisions have problems, but usually that avoids that gives the users the freedom of do whatever they want with the subset of subjects with acceptable quality. It doesn't put any restriction on where you can take the data afterwards once you accept it under certain constraints. Do you follow me?
Yes, sort of. But I think the problem with that, so yes, in principle, you can always, you know, have a very stringent threshold, assuming that the threshold is well defined.
Yeah.
But the penalty here, on which I think you'll struggle to have leverage on, is the penalty that you pay in losing data sets.
Right. Yeah.
So there's a trade-off there between the number of samples you've got and the quality. And in principle, you want to get this just right. Yeah, you want to be
right.
Optimal.
Yeah, maybe I should wait for the end of the talk to ask this question. You know, how can we account for the quality ratings broadly beyond this framework? I guess that's probably a question at the end of the talk. So anyway, it's been very interesting so far. Continue.
But I think so. The upcoming slides will probably answer some of your questions. I think it'll help to inform the discussion later. So that's the idea. It's basically like a summary of what we're going to do in principle, right? So now we're going to give ReML which is a very standard routine thing that analysis software do, with basis functions that are computed from the motion degradation index, and then we'll let ReML do its thing, okay, and compute the weights and things, and the rest of the analysis will be completely normal, okay. So just in a brief words, so the data will be dealing with, to illustrate the use of QUIQI is quantitative relaxometry data, okay. So the idea here is to estimate the MR parameters at each voxel in the brain, okay. So you can have different MR parameters, you can have T1 or T2 star, matization, transfer, a whole load of different parameters. And the value of this data is that the actual estimates voxel-wise are biomarkers of the underlying tissue macroscopic properties. So I've put a couple of illustrations of this. On the left-hand side here, you have a comparison between an R2 star map and histological measures of iron concentration in the same tissue. And on the right-hand side, you've got estimates of R1, so the inverse of T1 sampled halfway through the cortical layer, and the parallel with histological stainings for myelin density. So that's the value of this data, is that it gives you an insight into the macroscopic changes that might be underlying sort of brain change. Now, if you look at how these maps are computed, typically you've got the row of quantitative maps at the bottom here, and typically they are computed by considering the signal change across multiple raw images with different contrast, okay? So the thing is, for our purpose here, we're trying to look into how to assess motion effects and stuff. And in that case, it's a bit more complicated because it's, doing an analysis on R1 typically would require considering multiple raw image volumes, which complicate things a lot. So just for the sake of the current presentation here, so all we'll do is we'll consider R2 star maps computed from only one image volume and estimated using an exponential model across all the echoes. Okay, so that way we have a direct link between one raw image during which presumably motion took place and a corresponding map of R2 star. Okay, but it can be extended to quantitative maps computed across multiple volumes. So just a few words about the cohort. So it was acquired as part of the brain layout study, which consists of about 2,500 healthy subjects. The purpose is to look at the various risk factors associated with cardiovascular and psychiatric diseases. The MR data, it's the quantitative relaxometry protocol, which I just introduced, combined with a diffusion and a functional MRI experiment as well. So in terms of the motion degradation index, or what you could call it quality control measure, so I'll only describe it at the end, so I don't not to stop the flow of the talk, okay? But it's referenced, okay? So so we're dealing here with 1,432 data sets for which you can see the distribution on the left-hand side of the motion degradation index. The middle figure gives you the distribution of age, okay? Now, let's start with a standard analysis, so ordinary least square, okay? And when you solve a GLM. So on the top left, you've got the design matrix, a constant term, and then you have the variables of interest for our case. So you have an age and age squared, plus you have a bunch of confounding factors. You have sex, TIV, it could be anything in principle, okay? And then the colored images here, colored images here, they show statistical maps of the significance of the changes in R2 star with age, okay? So typically, if you look at gray matter, I'm showing an example time course with age here. You have a strong increase of R2 star with age due to iron accumulation there, okay? And in white matter, what you typically get is like the inverted U shape with a peak sometime around mid-age, okay? And the F scores, they are estimates of how significant the relationship between the data, so R2 star and age are, okay? Now, if you look at the trajectories here in the red boxes, you'll see there is a fair amount of noise in it, right? Okay, and presumably some of that noise will be attributable to motion artifacts. Okay, so the question we want to ask ourselves: Can we actually guess from the value of the motion degradation index the level in residual noise, and can we use that information to downweigh the data set that yield high model residuals? Okay, so in order to get there, we need to look at the relationship between residual noise after the fit and data quality as labeled with our index. Okay, so now this describes how we compute a global measure of image noise, so residual noise over the whole tissue type. So typically, so these colored maps here, they show individual residual maps after the fit. Okay, so you've conducted your analysis. Yeah.
Yeah. Can you go back to the slide, previous slide?
Mm-hmm.
Right. Were you referring to? You made a comment about MDA in the inside the distribution plots here. I don't see any information attaching MDI here. Was there any,
No.
or did I misunderstand?
No, there isn't any. So I was trying, no, there is no more information about the MDI here.
Okay.
This is showing an example of a change in the data, so R2 star with age, okay? And
Right.
pointing at the residuals, you know, the cloud of points around the fit, basically, okay?
Right. What's the legend at the top right? I can't read it. There is two type of.
In the box.
Yeah.
Okay, so this says, okay, so the gray plot, the gray dots are the data, okay, and the black is the fit. When you solve,
okay,
yeah?
my bad.
So
I was thinking you probably, yeah.
Okay, no, sorry, it's my bad. Maybe you can't see well. So, but the point is, so your model is the design matrix at the top left, okay? And you say, okay, R2 star depends on age and X squared and sex and TIV, okay? So you solve your problem and then you fit, this is the fit of the dependence of R2 star on age and H squared, if you like.
I mean, it's very interesting. TIV is taken as confound/covariate here. Maybe there is evidence to account for it. I can think about link of TIV linking to the motion, participant motion, but the link between TIV and R2 star, that is not clear to me.
That, I mean, often people put it in as a nuisance variable, so it's not something people would be interested in typically, but they use it as a confound to remove an interesting variance in the data, basically. So you see, you've got a lot of noise here. Okay, presumably the sort of distribution of gray dots around the fit. Okay, and presumably some of these residuals, they'll be coming from motion artifacts in the data. Okay, so
yeah, so I guess sorry to hold you up, but when you say there is a lot of noise here, that is assuming that everything that cannot be explained by the design matrix is noise, just like you mentioned before.
Yes,
right?
Yes,
I think that's a bit of a strong assumption, you know. I mean, that makes me think that we need to have established the distribution or the relationship between R2 star and age in a gold standard manner before you can consider what is actually noise or not. Don't you think?
That's true, absolutely true. I mean, in principle, I mean, this is not. I'm actually using. I mean, how do I say? The changes in R2 star with age is being studied before. Okay, so these are not really novel results at all. Okay, I'm not interested in the age effect here. What I'm interested in is the noise, but it's fairly established. I think generally when people do these things, they consider polynomial model typically of age up to a power of 2, maybe 3. I mean, I've tested 3 before. I didn't see any differences in the results.
But so I see where you're coming from, But the thing is, existing literature is often not very good, to put it mildly,
Yes.
especially because they haven't been accounting for quality very well.
Yes.
Do you agree? So
Yeah.
what I mean by that is basically, for example, for me to take something as a ground truth is, you have a very big and nice data set here. So a ground truth distribution for relationship between R to star and age would be, basically you have an external measure for motion, using infrared or various other techniques that you have. And just build the distribution only from people who never moved or moved so little that it wouldn't change. And then compare deviations from such ground truth distribution as noise. But I guess we are making a strong assumption that this somehow reflects close to what would be estimated if there was no motion at all, right? I mean,
I'm not sure what you're trying to say here.
I'm trying to say that the distribute, like basically the assumption that everything that cannot be explained by design matrix is noise is rather a strong one. Maybe others have comments on this,
Okay, so okay, I could find, fair enough. I think my answer to this, possibly. So yes, if there might be, okay, so there might be variance in there that would not be pure noise, okay, but the motion degradation index, which at the later stage I'm going to put in the analysis, is independent from that.
Okay, good.
So the variance of in the data that would be unexplained by the model won't be attributed to a different motion history either.
Okay, I guess
It will
that's what I was
remain. It will
missing.
remain
Yeah.
in the residuals. Yeah.
Right. Okay. Yeah. Maybe I'll wait for the end of the talk before holding you again.
Okay. No, you're welcome. So yeah, if you consider the level of residuals here, I mean, the chances are that some of these residuals will be due to just bad data. Okay. And the question that we ask is, okay, is there any way we can actually use the motion degradation index as a predictor of noise, if you like, and to downweight the data set that yield high levels of residuals? Okay, so next, so what we'll do is we look at the relationship between the residual noise and the motion degradation index. And to start with, so this is how we computed residual noise. Okay, so we did our GLM here like we did before. It's all the same, nothing different. What I'm showing here, the colored maps are maps of the residuals for one data set, out of 1400. Okay, there's plenty of them. Okay, and to have an overall global measure of noise in that particular data set, I just compiled the variance spatially across the tissue class. Okay, white matter or gray matter. Okay, so that's the measure, the global measure of residual noise that I'll be using. So you have one per data set and per tissue type. Okay, that is residual noise. And then we look at it versus the motion degradation index. Okay, and in the case of a standard analysis, this is what you get. Okay, so on the left hand side you've got gray matter, on the middle you've got white matter, and so these are plots of residual noise or variance of epsilon versus the motion degradation index. Okay, and you can see that for both tissue types there's a very coherent, strong dependence of residual noise upon the value of the motion degradation. Okay, so the motion artifacts in the data drive the estimates of the residuals. Okay, so I fitted these plot with polynomial functions, and the fraction of the variance of r squared here is typically 0.7 to 0.8. Yeah. Now, in terms of the statistics, that is a problem because it means that the variance is not uniform across your data set. Okay, it's called heteroskedasticity, and that is a breach underlying the statistical inference. Okay, because the variance in the data cannot be estimated accurately. Okay. So in fact, it's it just shows that there is a problem running a statistical inference, like running an F test or a T test on a data set, which is subject to such a thing, because it doesn't follow the assumptions, if you like. Yeah? Now, so what we're going to do, yeah, I could see you wave, but I can't hear you, Yaroslav.
We can't hear you, Eric. You need to use the right mic. I know you have like 20 of them connected. You're going to type it? Later. Okay, that's fine. Sorry, actually, another question. I think I'm just trying to, you call it variance of noise. Okay, let's wait for the end of the
where am I? So where did I say something?
No, it's okay. I'll wait until
okay, right. So here is that's our in the standard case of ordinary least square analysis. That's the dependence of residual noise at the global level versus the motion degradation index. Okay. Now we're going to, and as you see here, it fits really well a polynomial dependence. Okay. So what we're going to do, we're going to use that information in QUIQI by inserting basis functions, which I introduced earlier, which will show a polynomial dependence upon the MDI. Okay, so the first basis function will be the identity matrix for power 0 of the MDI. The second basis function will be a linear term in the motion degradation index, and then a quadratic term, and then a cubic term, etc., to mimic the relationship that we saw between the residual noise and the MDI. Yeah. And then that's what you get. So the top row is a duplicate of what I showed earlier, the strong dependence of the residual noise on the MDI, and the bottom row is what you get using QUIQI, and therefore like a weighted least square analysis, okay, for gray and the white matter. So if you look at the R square, so the fraction of the variance that's modeled by the sort of polynomial dependence that we use, typically you have R squared values between 0 and 0.2. Okay, so the overall noise level has decreased quite dramatically, but also, and more importantly, I think you're back to having a noise level, a variance that is uniform. Okay, and that you therefore restore the validity of the the homoskedasticity, which is a terrible word that underlies statistical inference. Okay. Okay, so one of the questions that you might want to ask, that we did ask ourselves, and that someone else using that stuff would want, is, okay, what components, what sort of component basis functions do I need to put into ReML? Okay, so I mean, we've built a toolbox in SPM to do that. For our case, we were considering polynomial functions only, so various powers, and then from the user interface directly, you can decide and try it for yourself. Okay, and in our case, so what we were asking was, okay, what powers of the motion degradation index do I need to model the noise optimally? Okay. And we came across, I think, something quite useful, which is called negative free energy. It's basically, it's a Bayesian concept that's used for model comparison, okay? And it's used for model comparison because it includes how well your model fits the data, so reduces the residuals, but also it penalizes the complexity of the model. So it's basically, if you have lots of different noise components, basis functions, but they don't explain anything in the data, it'll induce a penalty. So that, I think, is a measure which we found was useful in our case, but also I think beyond QUIQI and the rest. I think we'll touch on this later. It's one of these measures that might be very useful because they are quantitative and objective in the grand scheme of sort of assessing different quality control metrics or noise models. In our case, it turns out, a cubic power was the most efficient way of doing things. Negative free energy was the higher compared to the standard OLS case. Yeah. Now, amongst the physicists amongst you, I don't know if there are any, the nerdy physicists, but it's probably one of the slides that I like the most. And one of the, I think, questions that, might pop up is, okay, how well do you do correcting for local effects of motion on image quality, right? So on the left-hand side here, you've got, so we were comparing models, okay? So which optimal model of noise is the best for each gray matter region? So we repeated the analysis separately for each gray matter region, and we looked at which of the noise models was the best, okay? And what I like about this result is that, you can see on the cortical surface here, there's a nice gradient anterior to posterior across the brain, yeah? So frontal regions show a winning model with a higher power of the motion degradation index. And I think if you think about it, it makes complete sense. The motion degradation index, it's one value per data set, okay? So if your patients are lying on the, in the scanner table, with the back of the head sitting on the table, a given motion that would be described by the motion degradation index will have higher effect frontally, okay? And that's why the power here of the MDR is the winning model frontally. But if you look at posterior regions, well, then it's a lower power of the motion index that wins, okay? That's the first thing, which I think is very cool, because it gives you an intuition that you're actually picking something like plausible, like. And the second measure, which I think is very cool too, is the second plot. Same thing, if you look at the cortical surface, the gain in using that model compared to running a standard ordinary least square analysis is also higher frontally than it is at the back of the head, yeah, posteriorly, which I think also makes sense because that's where the degradation of the data due to the motion is the most severe. Anyway, I don't know if that got anyone interested, but it's the one I could.
No, this is fascinating, but I'm waiting to see how you compute MDI before
Okay.
Perhaps debating with you,
Okay, cool.
Because I would at least expect MDI is localized,
Yes.
Think about it, the head motion is somewhat rigid, right? Mostly rigid.
Yes.
Skull motion is rigid, but the brain motion could be semi-rigid depending on how much CSF they have on various other things.
Yeah, but I mean, in terms of sensitivity, I mean, to first order, I would imagine that head motion is a rigid body motion, like, and,
more or less, But what I do know from my subcortical analyses back in the day, like depending on presence of disease and whatnot, how big their lateral ventricles are, there could be a slight amount of tissue matter shift, so to say,
Right.
So yeah, I mean, we can assume rigid motion most of the time, but it's yeah. Either way, if you want to do such a localized analysis, I think we may need MDI to be localized. Don't you think?
That's right. So I know. Okay, I absolutely agree. But only I did this just for the sake of demonstration. I wouldn't recommend that generally, people would do regional analysis unless they have a good reason to. But it's just to answer the question of how well we're faring doing a global correction at the local level.
I mean, this also touches upon. Yeah, go ahead, Romain.
No, but even with a rigid motion, you have a local effect, as you just mentioned.
Yes.
If you move the head like this is a rigid motion, and you have more effect in front of the brain. So.
Yes, absolutely. And the winning model has a higher power, which I think is yeah.
Well, I mean,
yes,
Antoine,
but is it not as Prandi suggests a need to go with a local index?
Okay, that's a good point. In absolute terms, that's right. Okay, So in general terms, yes, that means because you wouldn't be able to conduct the combination of the basis functions at the local level wouldn't be the same as if you were doing it globally, okay? But in that particular case, I can do it because it turns out the winning model only has one component, it's the cubic. So you don't need to worry about mixing different components differently depending on where you are in the brain because there's only one component.
Yeah,
there's quite a lot to take, yes.
Yeah. So Romain, so there is, I mean, I'm yet to be convinced there is an effect, you know, so it's a claim from Antoine. So, right, well, let's say even if there is an effect, what is it, in a simple layman term, what is the effect that you're observing on the panel C here, you know? Are you saying that the WLS model accounts for noise better in certain parts of the brain where you see green here, right?
No, it is the gain. It is the gain in using weights.
Mm-hmm.
It's the local gain in using weights compared to running a routine ONS analysis.
Right, gain on what axis? Reducing variance, noise variance, right?
Noise gradients.
No, gain in reducing noise variance, right?
Noise radius, is that what you said?
Noise variance.
Radiance.
Epsilon. Variance, epsilon.
Epsilon. Ah, no. This is, no. So that it's using now the motion degradation index into the analysis, into ReML. Not the
right.
noise, not the noise residuals anymore. It's the motion degradation index.
Yes, but it's a gain in what? What
in free energy.
In free energy, okay.
So it's a Bayesian concept. It's basically the posterior probability. It's the probability of the data given the model. Or yeah, I think that's what it is. Okay.
Right.
So
but
it's the variable it's for model comparison. Okay. It's the trade-off between how well you fit the data and how many degrees of freedom you're using.
Yeah, yeah, basically that's what I thought too. So what that means is you explain R2 better, R2 star better with WLS model.
Yes.
In parts of the brain that are coded with green here, yes?
Exactly. The improvement is better in frontal regions because these are the regions that are the most affected in the first place.
Ah, okay, gotcha. So red is better.
Yes, because the increase is stronger.
Right, that's the thing, right? I mean, you're using a global measure to make inferences on local areas, right? So I guess we have to understand that relationship a little bit better.
Mm-hmm.
So for me, I think I may be a bit of an absolutist militant here. I think we may need, maybe we can use the data to develop a gold standard for that relationship and then use it to see if there is any local changes due to global motion.
I think what you're saying is absolutely right. It's, in general, I think just beyond QUIQI and the method itself, I think for the quality control group in general, I think what might be the most important is the approach. I mean, some of the metrics that are potentially useful more generally, or how to test quality control measures or noise models and things like that. Yeah.
Right. So I guess if I was a reviewer for your paper, what I would think about is basically, let's find a smaller subset of this data set where we know the motion is the least possible. Maybe like take 10th quantile, and then look at the relationship between R2 star and age, and then see if there is any local effect, right? Here we're mixing a lot of subjects that would basically confound many things, right?
Yes, I've done actually something quite similar.
Okay.
So that is I think it's the next slide.
Okay. Sorry, I'm jumping ahead too quickly.
That's all right. So we did a comparison of the QUIQI, the weighted least squares, with how people normally deal with a quality control metric. Okay. So, and in order to do that comparison, the first thing that we needed to do was determine what threshold we wanted to use, to discard the data. Okay. So the plots, you've seen these plots before. And it's residual noise versus NDI, nothing new here. So what we did, we tried discarding various fractions of the data with the worst motion degradation. Okay, so starting from the right, the higher the index value, the worse the data. So we did tests removing sort of 3% of the data, and then 7, and then 13, etc., etc. Okay, just to copy, sort of threshold values that people have used in the past. And in order to test for heteroscedasticity, we considered the R-squared values that I showed you before. Yeah, how much the polynomial fitting explains the variance in the data. And it turns out that basically in the case of gray matter, you need to discard about 30% of the data. So basically keep only the purple segment on the left here. Okay. To have a measure of heteroscedasticity that is similar to what you're getting with QUIQI, so between 0 and 0.2. Okay, and for white matter, and the situation is even more troublesome because even removing 30% of the data, you still have R-squared values around 0.4. So even removing 30% of the most affected data set, you haven't removed all the heteroscedasticity that is present in the data. So you might still have a problem in terms of statistical inference. Yeah.
I think I fixed my mic. Can you hear me now?
Yeah, I can hear you now.
And because that figure is again on the screen, so it just, while looking at white matter one, it's just not too good to be true. I don't know. But it's amazing that, let's say, so when MDI is low, people don't move, right? So there is no motion. All data points, and it's not like just one, right? But all data points, pretty much there is no variance, which is not explained by the model, which is really surprising to me, right? Because there should be unexplained variance, right? There is many factors which are not accounted for in that simplistic model, which is just age, what is this? I don't remember even if the weight was part of the model. So it kind of just, it's surprising to say the least, right? But then even if we take that it's true, well, presumably it's true, right? It's just amazing that then variance with the motion, it jumps not just like a little bit, right? It's like many times, right? Like 20 times more. I don't know even how many times more variance factor becomes higher, right? We go from, what is it, around 0, like 1, 2, to like 30. Yeah, so which is huge, right? So it just, for me, it's kind of not too good to be true, but it's a little bit surprising, and it makes total sense.
So one first to answer your question. So first, what the dimension that you're not seeing on this plot here is this is not a histogram. Okay, so typically 70% of the data. Remember, so if you look at the 30% case for that where removed, the 30% worst data sets are removed. That leaves you with the purple case. Okay, the purple dots are here. So 70% of the data is between 3 and 4 in terms of motion degradation index. Okay, so you could argue that in fact, out of 1,400 data sets, or so we're talking about what, 20, 30 data set maybe, so 1%. Yeah. Just to put things in perspective. Yeah.
No, I think the Yarek was saying something else. Basically, he's questioning the y-axis in terms of the magnitude. So if you think about like, typical Gaussian distribution that is be explained within 6 standard deviations, is that the thrust, Yarik, if I understand it correctly, like you have 20 or 40 sometimes, right? So I don't think we understand this y-axis very well to really take your important point, right?
Well,
So,
this is the variance, right? It's the square of the standard deviation.
Yeah, so that variance is teeny, right, when there is no motion, right? Pretty much in those data sets, which are purple, around 3 to 4, right? Especially around 3. 3 is a good number, right? So when MDI is 3, all those data sets, they have no, well, teeny amount of unexplained variance, right? And I'm surprised how that could happen, right? What is that unexplained variance? Is model really explaining it that well that there is not that much of variance, right? So it's kind of became a little bit bothersome to me. But also when I was looking at the original plot, you can see that this funnel, right? It's pretty much like bound by two like lower and upper lines, right? Which kind of spread out, right? And nothing kind of in the white matter case. In the gray matter, it's more realistic, although you could also see kind of lower bound, which also makes sense, right? So if there is noise, you're guaranteed to have some variance, right? Because motion will introduce variance. But in the white matter case, it was really kind of really striking that, oh, there is upper bound and lower bound, right? So it's too good to be true. It's so nicely kind of.
I mean, okay. So in terms of, ultimately, I know the data. I've done it myself. But in terms of the range, okay, let's start with the range. So it's basically, if you consider, well, this is 3 Tesla data. We're talking, okay, it's like an R2 star value typically like 20 times a second. Okay. Yes. So take the variance here being 20, take the square root of this, we're talking 4. Okay. Yeah. So
yeah, that
would be a standard deviation of 4 when the mean is 20. It's not that crazy. I mean, given that these are the worst data sets, like.
Right. So for those without MR physics background, can you quickly explain what does R2 star measure? We know T1 weighted measures tissue properties, tissue contrast. What is it optimized for?
So
it's pretty much, if I explain it and you tell me that it's wrong, right? So that's exponent component, right? When you explain it, going through different echo types.
Yes, exactly.
Right? So there is this exponential decay rate, right? And the presumption is that for different measures like T1, T2, that exponential decay rate should be different, right?
No, my question
or
is
should it be
basic.
The same?
No, that's so R2 star. I mean, at least for what we're concerned here, I think we can safely argue that R2 star is independent of the raw image contrast.
Right. So give me a physical visualization for what does it measure, like real layman.
So typically, okay, say let's take you're sitting in front of the scanner, okay? You use you acquire data with a short echo time, okay, as fast as you can, like 2 milliseconds or something, okay? And then you repeat the acquisition with a longer echo time. So before you acquire data, you wait longer, okay? Well, what happens is, going from 2 to 10 milliseconds, the signal decays. You have less and less signal. I mean, ultimately, if you have a very long echo time, you'll have no signal left. Okay. So the longer you wait, the more the signal intensities drop. Okay, and the rate at which the signal drops as the echo time increases is R2 star. It's the rate of decrease of the signal with the echo time.
Is that expected to be different for gray and white matter?
Yes, I can show you.
Because there are different issues, right?
Yeah, that is a map. I can probably show you a better one. But typically, the areas that show up are subcortical areas like the pallidum or the putamen, because they are iron rich. Yeah. So locally, they induce a dephasing that leads to a signal loss, or sort of heavily myelinated fibers can have an
Right.
impact as
So
well.
I guess that also comes into question, you know, the change in gray and white matter properties. Do we expect them to be different for different types of motion, or at the same level of motion? Right? Do you expect different R2 in gray and white matter at the same level of motion?
You expect the same level? Are you asking if the motion?
Do you? My question is, should we expect different values of R2 for gray and white matter at the same level of motion? Right? Because a lot of this discussion, the assumption lies is that the gray and white matter behave differently at the same level of motion.
No, it's not really that. So we consider gray and white matter separately here, because the way, so we're working, and then also that might answer one of Yaroslav's concerns here. So we're working, this is a group level analysis. So where you've sort of merged the data into a group space, right? And in the process of distorting the image into a template space, it's basically it separates white and gray matter because they have very different properties, in fact, and you don't want to mix them in the smoothing process.
Right. Yeah, that I understand for T1 and T2, for example. I'm just trying to understand if that applies to R2 star as well.
It's yes. So here I'm treating gray and white matter separately, not because I'm expecting different effects of motion on them. It's just because they really are separated in the process of normalization.
And do you get this segmentation from a T1 that is acquired separately?
No, from the MT maps, which is a map I'll show you here.
Right. Okay. I remember that. Yeah.
This one here. Yeah, because it's got a good contrast.
Very interesting.
And I think so, Yaroslav, oh, I'm going the wrong way. So to go back to your skepticism, I mean, okay, so in terms of the range, I think this is not, where am I now? Yeah.
Yeah.
Yes, so it's basically, so you know, an R2 star value at 3T is typically roughly just order of magnitude, right? 20 per second. Yeah. So say if you assume a variance of 20, you take the square root, will be 4, 5, something like this. Yeah. And that,
yeah.
that is,
Yarik, I think maybe I can explain maybe I can try answer your question. So basically, the important part is here is the measure itself, which is the R2 star. And like one of the things that Antoine mentioned earlier was that there is a well-established relationship between them, right? Between R2 star and age, right?
yes.
Which I guess I would like to double check with a ground truth data set where there is no such motion at all. Assuming that is true, basically like he pointed out, variance is the square of SD, and which 0 to 6, which comes back to 6 squared is 36. So the axis is not all that surprising in that sense, so long as we assume that R2 star is all but well clearly explained by age, sex, and TIV, right? So that is the strong assumption, right? So that makes sense, Yarik?
Sorry, my headphones fell off again right when you were speaking. So I missed like last 2 sentences.
No. So basically there are 2 strong assumptions in the whole analysis, which is that there is a well-established relationship between R2 star and age, right? That is all clearly explained by age, TIV, and sex, right? And that the relationships we see here will also be preserved if there was no motion at all, which can be probably checked in this data set. Go ahead.
Something like that. And also my comment could be flipped the other way. So it means that if there is no motion, right, the entire variance in R2 star is well defined. And the rest then, well, pretty much there is no variance in its estimate, right? If we take the leftmost points, right, that variance is teeny, right?
Yeah.
So it means that if subjects don't move, right, so MDI is low, R2 star is great, right? So there is little tiny variance.
There's something, okay, maybe another thing that I didn't mention. At the group level, that data is smoothed. Okay. To overcome potential errors in the spatial transformation. Okay?
Right.
So there's always.
That's okay. That's okay. Even
that
with
explains why
smoothing.
the variance would decrease. Okay, maybe
Sure. It will contribute to the decrease of variance. Yes, but the variance here is across subjects, right? Not within subject, right?
No. So variance of epsilon is computed for each individual data set.
And by each data set, you mean subject,
Image.
participant,
Yes,
image.
Exactly.
Okay.
So
it's across.
So look at, okay, maybe that'll clarify things. Like, look, so I've got, so this is an example of residual map for a subject, okay? Yes. And then I pull spatially across white or gray matter. Okay, so the variance is within a subject here to capture potential changes in autostar due to motion.
Right. Yeah. So I guess basically
got that. So,
yeah.
But smoothness will decrease it, right? So it will kind of smooth it out, right? So variance will become smaller, but still because of the rate of change of that variance, even with, because you smoothed all those data sets equally, right? I mean, to the same degree, right? And in some subjects which have no motion after that smoothing, pretty much R2 star is well defined, right? Variance is teeny across spatially within that image, right? And then you're fitting another polynomial or exponential with those 2-3 components, right? Trying to explain it. But I wonder, so we kind of defined that if there is no motion, it's well defined, right? So there is teeny variance, right? And then variance kind of grows as motion grows. And we know that motion is not really linear transformation of the image, right? It's because it does all kinds of shit. And I wonder if we could come up with maybe additional explanatory variables which will provide actual explanation to this, why it's much higher, let's say in one subject and image, right? Even with the high motion, right? So we have, they go from like 35 down to again like 5, right? So that's again huge thing. So why? So MDI itself is really gross measure, seems to me, right? But let's say maybe if subjects just moved like laterally, I don't know how to say it, up and down, right? That would be one type of motion which might not be introducing those big variance effects, right? Because who knows, right? I think looking deeper into what constitutes that MDI value and taking those might provide you pretty much exact model, not exact model, but to account for this variance, then just gross MDI factor. That's pretty much my.
Yeah, maybe we should get into how MDI is computed. I think it's coming, right?
Yes. Okay. So again, I think I agree. So your point, there might be more to this here. There might be an underlying variable which explains another dimension. That's possible.
And also a message that the motion is really, really drastic, right? I mean, has drastic effect on this R2 star, right? So motion is pretty much the only thing which drives it when you account for age and whatnot, right? Because variance is teeny.
It's not quite the same, because remember, so this is a global measure pulled within a subject, not across subjects. So this doesn't show how much change in R2 star was present in that particular case. But
if you take any spatial map of R2 star, right? If subjects don't move, there should be little to no variance, right? So all white matter should have the same R2 star.
No,
right?
no, because it varies with age.
You said that, that's separate, right? So age is across subjects.
Okay, so
But here we look at,
if you did trend it for age, yeah, then there should be no difference in R2 star anymore. Yeah, okay.
so pretty much age, what else was there in the model, right? Age and what those parameters, right?
Sex and
They
TRD,
should, yeah, so they should provide really nice explanation for any of this R2 star thing. And if there is extra variance in R2 star, it's due to motion, period, right? Because it seems to me that's what we are observing from this figure. There's little variance if there is no motion, and if subjects move, that's it. That's when stuff besides these basic demographics, right, introduce this huge range of variance, right, in unexplained, I still don't want, like Pradeep, I don't want to call it noise, but unexplained variance of R2
Yeah.
star.
No, I think that's exactly right. That's how I'm thinking about that too. We see this effect because we chose to condition them on only the few things that we care about, right? So it's a bit of a selection bias going on here. Actually, in fact, I've been working on developing a library called Confounds to help answer these questions. A big problem in this space, as we have learned now, is to decide what is a confounder or not in your particular question, data set, and analyses, right? So there is a lot more that can be done here to establish that the variance we see here is caused just by motion alone and nothing else, which I think is a strong assumption, right? For example, we didn't measure respiratory data, right?
Well, that one I bet correlates with the motion, I bet, right?
yeah, it does, but there may be that the big variance we see for MDI-7, for example, could be coming from both motion as well as other things which are not even measured, unobserved latent factors, right? So anyway, I want to see the definition of MDI so we can actually better drill down to where it is coming from.
Okay.
But this is fantastic. Don't take this as criticism, Antoine. I really like what you've done so far.
No, but that's good. I mean, I need to think about it, but yeah, I'll have a think.
Well, how many TEs did you take? And how does it extend, let's say, how could I sell to my imaging group, right, that don't just get T1 weighted, right, get T1 weighted multi-echoes, within it. We are trying to do the same for EPIs, right, for fMRI, to do denoising. It's pretty much the same, multi-echo EPI, right? And here it's multi-echo T1, right?
Yes, exactly.
Does it extend acquisition? Definitely it extends, amount of data you need to store, but does it take much longer?
So it's flash. It's a flash sequence. It takes for 1 millimeter resolution whole brain takes about 7 minutes per volume.
With how many? Oh, you do them separately, different echo
so
times.
The way this works. So we do it consecutively. So that's the raw data. Okay. So so they're all flash acquisitions. And only basically the flip angle changes. Yeah. So you get, for each contrast here, you get 6 to 8 echoes depending. Okay, and so you can do an R2 star estimation separately for each of the raw image volumes. Although in practice you wouldn't actually do this, because you would probably pull across all contrast to improve the signal to noise.
But the point is that you just do separate different TEs, echo times acquisitions. It's not like some magical sequence.
Okay. So the echoes are acquired simultaneously after each RF excitation, and you loop around for the encoding separately. So you acquire one 3D image in 7 minutes, and that gives you all the echoes. And then, yeah, does that answer your question?
Yeah. And does it introduce extra penalty? Let's say if I were to acquire just single echo, it should be the same, right? It should be the same
Well,
time.
if
Besides
you
that,
acquire a
I
single
want.
echo, I mean, if you acquire a single echo, I probably wouldn't recommend it because I suppose you would make the repetition time very short to save time, right?
But isn't that what we typically do when we acquire T1, right? We
But
get
it
just
depends.
single
But it
echo.
depends. I mean, the repetition time in the context of an NP-range acquisition means very different. Means something different than here.
Than Flash.
So,
Yeah, so I need to read more about that, but it seems to be beneficial to acquire then Flash sequence, right, with multi echoes, multiple,
yes,
expanding some specific range, which goes from 5 to 20-ish, right?
yes. If you want an example of like a reference, go take one of these, Weiskopf 2013 or Lutti 2014. You'll find the info. Yeah, so typically the echo times lie between 0 to 20. Yeah.
Yeah, so actually we need more education in this space, Antoine. You know, if you can find good experts talking about various trade-offs with different parameters in MR physics, that would be fantastic, you know?
Yes, but I think you make, genuinely, so I mean, I've been doing quality assurance and quality control for quite a long time, but I think having input from the physics, I think, is important.
Yeah, I emailed Nicholas Wiskoff to try to give a talk, but he seems too busy. Maybe I'll keep pestering him.
Well, I know Nick, I can have a word, or maybe I can help anyway.
Yeah, so the paper you referred to, you know, 2013, you know, basically in this space, explaining how different parameters interact with each other, you know, trade-offs between multiple echoes, single echo, longer TE, lower, shorter TE and whatnot. See, for physicists like you, I mean, I have a physics degree, but I don't think I'm very good at MR physics, you know? So for many neuroimagers and neuroscientists, this is just, but they just don't have this understanding at all, you know, of what data they're working with, right? So giving them some high-level layman terms of explanation would be fantastic, you know. If you can help get some experts to give a talk, that would be fantastic.
Yeah, sure. We can certainly arrange it. Yeah.
Yeah, great. Thank you. Now, let's get to MDI.
Should I just move on? Or say,
yeah.
Just one point which I thought was quite interesting. So in that table here, yes, so the bottom line was using that R square measure of heteroscedasticity. Basically, in gray matter, you need to remove about 30% of the data to ensure statistical validity. In the case of white matter, you just can't get there. Yeah. So when you look at these F scores, these are the sort of the significance of the aging effects in that analysis. So we use that as a measure of sensitivity because the F score is basically a ratio of the model variance versus unexplained variance. Yeah. So ideally, you'd want to have an increase in F score would show an increase in sensitivity, right? So here we do the comparison in gray matter because we know that even for the exclusion analysis where we just remove 30% of the data set, with the noise is homoskedastic, okay, and then you can see the higher F scores produced by QUIQI. In the white matter, we just don't do it because we know, based from the previous slide here, that the noise is not homoskedastic for the exclusion case, if you like. Okay, so now there you go, Pradeep, shoot. So this is about the motion degradation index. So I thought I'd keep that for the end because you didn't flow in the rest of the story, right? But I appreciate that it's important. So as a measure of the motion degradation, we use the standard deviation of RT star in white matter. Okay, on the premises, at least the original motivation was that the noise typically would increase variability within white matter, and that doesn't really come out of the blue. So that's from a paper that we published a couple of years ago, more than that now. So what we did, which actually that touches upon another point I made about empirical validations of motion degradation indices. So what we did, we conducted a study comparing the index, the image-based index of motion degradation versus the actual history of the motion during the acquisition of the data. Okay, and we did that by using a camera system where you'd have like a camera sitting in the board of the machine and watching people the entire time. Okay.
Can you define motion history?
So motion history is a combination of head speed and k-space location, okay, aggregated over the duration of the acquisition.
Okay, so it's like total sum of displacement, roughly.
Sort of weighted by where you are in k-space at the time of occurrence of the motion.
Why is that important? The location in k-space?
Because you might, depending on when you move in, relative to the acquisition, the effect of a given motion on the final image will be radically different depending on where you are. Okay? So typically, if you move at the center of k-space, where most of the signal is acquired, if you, might move the smallest amount, and the image will be rubbish. Okay. But that's something that we demonstrated here in the paper. Okay. But then if you're outside k-space where there's little signal anyway, you might actually get away with quite a lot of movement. Okay.
Right.
And that's what that motion history does. It combines both. Okay.
One more question.
In fact, you'll see how beautiful it's one about. We actually pushed it one step further in that paper. Okay, because that we had that nice relationship between the degradation of images and the history of the motion. Okay, so what we do in real time, the scanner, we compute that motion history in real time. So for every 20 milliseconds, we compute the head speed, knowing where we are in k-space. Yeah. So as soon as you move, we can predict how much degradation that movement will lead to. Okay. And based on that prediction, you can decide to go ahead with acquiring the data or suspend it. Okay. So the scanner stops. So the carries on running, it keeps, the grains are still on, the life is still on, everything, but we don't acquire data, okay, until you stop moving. And when you stop moving, the machine resumes automatically, okay. And what it does is typically, so you have that threshold value that determines beyond which the scanner will suspend, okay. And depending on the threshold value that you use, if the threshold is quite lenient, like the red dots, well, you restrict yourself to a fairly broad area along the blue line, which was obtained without suspension. Okay, but then if you use a more stringent threshold, like a smaller value, then the suspension will trigger more often. Okay, and you stick yourself, you stay near the origin. So no matter how much motion, how much you move during the acquisition, because you use a stringent threshold, you're close to the origin. Yeah. And the predictor, and in fact, it's actually quite efficient, because not only do you account for how fast you're moving, but also where you are in k-space. If you're moving a lot outside k-space, you'll keep acquiring data, and you end up just extending the data acquisition by a few percent, and it makes a difference between a terrible data set and a largely usable one.
Great, thank you. I have two questions actually. One being, you keep referring to image degradation, right? I mean, basically that assumes that any motion degrades the image, and are you measuring motion or degradation? That's one question. Actually, maybe two more questions. Second is, the definition is based on white matter, right? If you go back a slide, it's all right. So, but you then will analyze variance in white matter. It's a bit circular there, right?
Yeah, okay, I was ready for that question.
And the third is the validation you show here, MRM 2018 paper. what's the age distribution of this data set, and how does that differ from the previous one we were looking at?
Okay.
Because basically what I'm getting at is, yes, okay, you may have validated it here. Let's say if you did it in nice and healthy 20-year-olds who can just sit still for 20 minutes, and we're looking at the entire lifespan. So maybe that relationship will not hold, right? And we know because age changes a ton of things. Actually, the younger ones move more, the older ones move less. So at least from what I understand from small fMRI data sets, which may not be true for everyone, you know. So yeah, that's three questions.
So the first one is about image degradation versus motion degradation.
No, I mean, you keep, that's the thing, right? MDI is measuring degradation or motion. That's the question. Basically, are you using them interchangeably, you know?
Okay, so maybe I did, in which case I apologize. But so what we did for most of the talk, yeah, we were looking at the image-based measure only. So it's the vertical axis here. Okay, we don't know what happens in real time during the acquisition of the large data set. The point I'm making here is that we had conducted another study prior to this, where we compared the image-based marker versus the physical motion, if you like.
Right, no, that I understand. My question is the MDI like FD, you know, frame-wise displacement that you compute in fMRI, which is actually strictly measurement of motion, right? Is it just motion alone, or is it the effect of motion on the image quality, which is what you describe as degradation? Do you follow me?
So it's not motion per se, because you have one image. So for one R2 star map, you have one image and multiple echoes. Okay, so you wouldn't have you have only one image, so you can't measure motion, you can't do a realignment procedure or anything like this. So it's really an image-based measure of the data itself.
Okay, yeah, now I understand. It's not motion. It's
No, it's not motion.
Yeah, it's suspected degradation, right? So yeah, there is two big assumptions, I guess. Then, you know, you're using the white matter data to estimate it, and you are assuming that is due to motion alone. And then you make that assumption again in the decision matrix because you're only including age, sex, TIV, and nothing else, right?
But okay, so hang on. So I'm not putting the MDI in the design matrix, if that's what you mean.
Yeah, you're not, but basically you're saying in our universe, think of our vector space, there is only age, sex, TIV, and motion axes, right? That I guess, and anything that's not explained by age, sex, and TIV is assumed to be due to motion, but we're not measuring motion. It's right. It would have been fantastic if you had some external measures of motion here, you know.
Yes. Yes. So, but it's okay. So, like I said, so right. So, yes, in principle, anything that might have an impact on the R2 star values that are not in the model will contribute to variance. Yeah. So I think to get a feeling for how much that might be, I mean, I would probably consider a change in R2 star due to a potential confounding factor, which I wouldn't be modeling. So referring back to the literature, compared to the changes in R2 star due to aging. Yeah. But to be honest, I haven't gone to that exercise.
Related question, while this curve is there, did you ever look at the residuals from the feed here, right? Because you need to feed across those points to get R2 star, right? And I think there is this pretty much closed relationship between if you move, right, your feed here would be worse, right? So that variance maybe then explain the variance you see in those R2 star at the higher level, right? That model which we talked about.
Well, so that's done. We've published something on actually computing weights from the sort of contrast specific R2 star estimations. Yes. The problem with that is so there are several problems, but the problem is, so this is done at each voxel. Yeah. And you can't, so hang on, you can't, normal statistical analysis routine wouldn't let you have voxel specific prior on the noise distribution, if that makes any sense.
That's probably okay. But I'm trying to lean forward toward, let's say, with the motion, right? Those echo times, they occur at different times, right? And if there is motion, then there is a shift, right? So then fit here will be less clean, right? So if it's a perfect voxel, then it should just follow that trajectory, right?
Yes.
If it moves, right, then you would get motion related variance in this curve, right? And that unexplained variance here might be the actually, when averaged or anyhow aggregated across voxels in the brain, might provide you the measure of motion, right? That's what I'm thinking. Maybe it could be.
We actually, hang on, do I have the internet here? Yes, because we looked in the MRM paper. It's got, I think these are in the supplementaries. We looked at this. Hang on. MRM 2018. Do you see my screen?
Not yet. No, you're probably sharing only PowerPoint.
Ah, yeah.
Stop
okay.
and then.
Yeah. Hang on. Let me try and find that figure fast.
Actually, also maybe in the interest of time, perhaps we can finish the rest of the talk if you have any.
Yes, but to answer the question, in the 2018 paper, we looked at motion history versus residuals exactly on that basis, and it tends to follow the same dependence.
Right.
So that means that we don't need any fancy history, right? We could just use variance theory if I acquire a multi-echo thing, right? And to judge either, oh, there was lots of motion and anatomical or not, pretty much, right?
So okay, in general, that's what I'm trying to say here for the particular case of the cohort here. So what we're using the motion-based marker without knowing the history, okay, based on this empirical validation. Now, so what we've done here for the sake of this study, I think that for in the more general term, it's something that you could replicate with different data. Now, the different data, say MP range, images are encoded completely differently. So motion artifacts might manifest themselves differently, okay? And there might be other measures that are more suitable, say, yeah? So so I'm not saying that looking at the variance of R2 star in white matter will, is a solution for everything. Yeah, but what we found is it works really well for sort of multi-echo flash data. Yeah.
Yeah. So in the interest of time, let's finish with the rest of the talk. If you have any take home, perfect. Let's go.
Yes. So what I was presenting here, so it's basically a novel approach to handle a quality control index in the analysis, because I think so far, and correct me if I'm wrong, but I think the standard is still to sort of dichotomize your data set into two subsets. Yeah. I think so. What we show is that I think it's more optimal to assign a weight for each data set based on the motion degradation index, because you can find a better compromise between the number of samples in the study and the corresponding quality, if you like. Okay, and it also ensures the validity of the inference that you might want to make on your data. So it's actually quite amenable, I think, to various types of MRI data. You might consider other types and other matrix too. Okay, so we've got we've got an add-on to an SPM toolbox that does it. Okay, and that lets you decide what sort of how many powers you want, or potentially you could have a different model of noise altogether. We use polynomial because we thought we could see that it sort of fitted the data. And also, I think beyond QUIQI, I think the point is that I came across thinking about this, that it provides a bunch of measures that are actually quite useful and can help to sort of as outcome measures for either for quality control metrics or also for motion correction metrics. And this looking at heteroskedasticity and making sure that the data is suitable for statistical analysis. You can do it globally at the voxel level. Free energy is also really useful for model comparison. So these are things that you could use or base yourself in order to compare the performance of other different motion correction techniques, or also to look at the heteroskedasticity of the noise along multiple dimensions of the quality controls, for example. So I think these are, this could help to sort of put number to things a little bit, which is quite difficult. Like, okay, I'm done.
Fantastic. That was a fantastic talk, Antoine. I think we had a ton of very interesting discussions and a lot of back and forth and whatnot. So any questions?
You've challenged me. I liked it.
I am sorry. That's coming from a place of love, Yeah. Any questions, Romain, Sivania? We have an exciting new participant here, actually. Okay, she doesn't have any questions. Romain, go ahead.
No, thanks. That was good. Just to be sure, I follow how you compute your image derived index it's related to this variance within the white matter, yes?
Yes.
From
this
air
is
to
specific
star.
to this is specific to my data, right?
So it's specific to this air to star computation.
Yes, exactly. And it's also, and I like it because we've done this work of comparing against motion behavior. See, which gives me a lot of confidence that we are, although we don't know the motion history now, we're safe sort of computing from the images directly and using it as a motion degradation index.
But the way it works, it's because this air to star measurement is very sensitive to motion. That's maybe why you find a so good correlation with your real motion from the camera.
Well, yes, possibly, yes. So reason why it would be. That is one, presumably. Although, having said that, I mean, I think motion artifacts tend to get worse with increasing echo times, and the echo times here there wasn't one particularly over the roof. I think it was about up to 20 milliseconds.
Okay, thanks.
No problem.
The question I asked before about how does the age distribution in this particular data set differ from the other validation paper from 2018?
Okay, it's very different. So
right. So that's something you might want to look into, see whether that validation applies to this data set, right?
Yes,
and that also, sorry. I mean, that also touches upon, can we use phantoms to study this, to take the humans and motion out of the equation to validate whether, well, I don't know, but I guess we need motion to study it. Sorry, I take
the problem, you see, so it's always a catch-22 situation, because if you do something on phantom, you'll have the problem that you're only simulating real motion conditions to some degree, and ultimately, you might have a problem convincing people that what you're picking up with a phantom is a genuine.
No, so basically where that is coming from is the need to validate the variance in white matter is actually what's the word, faithful to actual motion. For example, you might have seen this paper on dynamic phantoms we shared with the group, right? That phantom would allow us to introduce known amount of motion in known directions, right? And then if you use external trackers to see the resulting motion and then capture that variance in R2 in certain parts of the phantom, that would help validate R2 as a way of an image derived estimate of motion in a way, right? So that's where I'm coming at, right? I mean, you trust it to be, but I guess we're just trying to kind of be the devil's advocate,
Yes,
Go ahead,
yes.
No, man, you use the right mic.
Zoom. It makes me quiet all the time. I don't know. You can hear me now, right?
Maybe you criticized Xi Jinping of China, and then they're making your life harder.
Yeah, everybody's making my life harder, I wonder if those multi-echo images could be used to assess, let's say, in plane motion, right? Because you have them and you could just do even probably least square feet between them to get the assessment either within this minuscule time was any motion, although maybe it's too small of a time, right, to make judgment, but so it will be what difference of 15 milliseconds, right? So it's probably tiny.
But it's also the problem with that is that so these images are 3D encoded. So you don't get the data one slice at a time. You encode, especially with gradients, the entire volume, and you get no image until it's finished, if you like. So you get a whole 3D image after 5 minutes, but slices don't come sequentially like they do in functional imaging, for example.
I need to read more on that, what happens indeed. So it will not be possible then to, okay.
No, so the way what we did was we used so that the camera system, which is it's a nice kit. It's not easy to use, so it's not used in the lab as much as I'd like it to, because it's finicky, but it gives you motion information at a frequency of 50 hertz or something, with a lag of 20 milliseconds, roughly speaking.
Yeah, so this has been great. I think what would be super well received in OHPM community, at least, is similar framework applied on fMRI type of data. Right, because I think that's what people would have, I mean, my guess is that if you have a way to account for motion in statistics, which is the rough thrust of the work, because fMRI, it's a big pain and they would want methods to do that, right? So I would highly encourage a subsequent paper or another analysis on this, on some type of fMRI data where estimates of motions are available,
I think,
but isn't it directly applicable? Isn't it directly already applicable? I thought it's just,
No, it is applicable, right? It is applicable. I'm just suggesting Antoine do it and actually make the case that it is possible to do it and it helps in a real way. Right now, I mean, there is a few circular things here, right? If you used FD in place of MDI, it reduces the level of attack surface on the work in a way. Or if you used external motion estimates, like the infrared and stuff like that. That's where I'm going with this, right? And also making it fMRI, it attracts all the neuroscience crowd. I mean, what you call cognitive science crowd.
Yes. I see where you're coming from, but I don't know the literature in fMRI because I haven't done any for quite a while now. I know Nick Todd, so similar to this. In fact, the motivation for considering this, looking at the standard deviation of R2 star it came, hang on, was it? I have the impression that, you know, so Nick told, so the group that I was part of in London, they did something in functional, for functional studies. Now, but you see, the funny thing is all that stuff, the big ReML, it's people in functional studies, they use it all the time. They what they do is, because they often have problems of non-uniform variance with a group that would be a patient cohort, and they move more and yeah. So that they do very standardly. So I think potentially the use would be, now if you had weights, that would be subject specific. But what I don't know is what MDI measure you'd use there. I have no idea, because I have no guarantee. You wouldn't even be able to compute the MDI, this MDI in that case.
Right. That's why I was suggesting FD, framework displacements or DWARs or similar metrics. You know,
Yes. Mm-hmm.
so DWARs is probably the corresponding metric in fMRI, right?
Mm-hmm.
I think that would be very interesting, you know, especially if you do it on an open data set and share the analysis scripts. We can, I'll try to help, you know. Yeah.
Okay.
Any comments, Jarek, before we close out?
Not enough comments from me. Come on, man. We're past the original time.
Yeah, this has been a fantastic Antoine. This is awesome. This is great work.
Thank you.
Thank you
Thanks
much
for the feedback.
Yeah.
Sorry, I disturbed you during Labor Day. I wasn't aware.
No, it's I mean, it was my mistake. I should check that. And big thanks to Jarek for showing up for every talk and also sticking with all the good comments. Jarek, I didn't realize you're such an expert on imaging acquisition. You know, I thought you were more of an informatics guru. My bad. You know?
I am not an expert in anything, and I need to fix my house. You know.
Yeah. Anyway, all right. Thanks so much. Let's keep going. I'll look at the papers that you mentioned, Antoine, and please feel free to drag me into anything you need. You know, I'm happy to help out. This is fantastic work.
Yeah, thank you very much for the feedback. I really enjoyed the conversation. I had a great time.